the next topic, which is ready for today's class, it's the hyperbolic circles in U. So I'm going to describe the hyperbolic circles in U, and then I'm going to go back to study the Riemannian isometries of the upper half plane to give now full descriptions of the isometry groups. Right. So, but hyperbolic circles, right? Because if we already studied the shortest curves, which are the notion corresponding to straight line, the model, well, kind of the next thing that would be nice is to give a description of the circles. Yeah, and so for that, I'm going to first establish an explicit formula for the distance, similar to what I did in the hyperboloid. And to do that, I need this lemma, which is that this function is invariant on their PSL2R. Right? And what I mean is the following. So this is just the norm of complex numbers. Right? So norm squared, and of course this is imaginary parts. Yeah. And so what I mean when I say that this function is invariant under PSL2R, what I mean is that if you take 2 points, if you take W and Z, and you take this expression, and on the other hand, you take any element nu, in PSL2R, and instead of W you write nu W, and instead of Z you write nu of Z, then the value of this expression is the same, so that this is equal to nu of W minus nu of Z image nu of W image nu of Z. Right, so that's what I mean by this, right? Similar to when we spoke about the cross ratio. Right, so this formula, the value of this doesn't change if instead of W and Z, I take nu of W and nu of Z, where nu in PSL2R is arbitrary. I leave it as an exercise. Yeah, it's just direct computation, because you see in the previous class we learned how to compute this imaginary part. Okay, and now using that, I'm going to prove this formula, which is also I think a very nice formula. And notice that here what I'm saying is that the hyperbolic cosine of the distance between 2 points is 1 plus precisely the value, this value. Okay, so for this theorem, I'm going to assume that this lemma has already been proved, so that you already did that exercise. Yeah, and that somehow that gives me a lot of freedom, because somehow the idea is that I know that for any 2 given points there is one Mobius transformation placing them in the vertical in the positive part of the imaginary axis, and so I'm going to do the computation there. And since my expression was invariant, that would allow me to go back. Okay, so when I'm situated in the positive part of the imaginary axis, and actually, you see, I'm situated at the point I and at the point lambda I, where lambda is greater or equal than 1. So it's kind of I and then something above, right? This can always be done, right? I mean, up to applying a transformation, I can always send my 2 points W and Z to I and lambda I for some lambda greater or equal than 1. Okay, and then here, the hyperbolic cosine of this distance is the hyperbolic cosine of the natural logarithm of lambda, right? So because of by the formula from the previous lecture, that that the distance between AI and BI was precisely for b greater than b greater than a was precisely the natural logarithm of this divided by this. Right? So here is the natural logarithm of lambda divided by 1. Okay. Now hyperbolic cosine, it's given by the formula, right? E to the whatever plus e to the minus whatever divided by 2. Okay, but well, we know that the exponential is always introduced as the inverse of the logarithm. So lambda plus 1 over lambda, right? And I just developed this, right? Kind of to have only one denominator instead of 2 appearing. Yeah, and then here somehow here you see, since I know that I want a 1, I force the 1, and the way I force it is, you see here, to force it I add plus 2 lambda over 2 lambda minus 2 lambda over 2 lambda. This one becomes this one, and this one becomes this square. Okay, and this is, well, the one I just write it on the left, and here you see this is precisely this, and right, because when I take just the imaginary part, is just lambda minus 1, right? Square, and this of course lambda is the imaginary part, and 1 is the imaginary part of I. So at least for these 2 points, the claim is true. Right? So the theorem is at least true for W equal to lambda I and for Z equal to I. But as I said, any 2 other points, Z and W, let's say, yeah, W and Z, can be sent to lambda I and I by some nu in PSL2R. Okay, but somehow, but you see, this expression doesn't change if I replace lambda I and I with nu inverse of them, right? And also every such nu is a Riemannian isometry. So in particular, it's a metric isometry. It preserves distances. And so again, if I replace lambda I with W and I with Z, this distance doesn't change. So the theorem follows. Okay. Now, so this is I would say a really nice formula. It's again hyperbolic cosine of distance. And I'm going to use this to describe the hyperbolic circles in U. Okay, so to describe them, let me use this notation. Whenever I'm speaking about an Euclidean circle, it's going to be with an E here, and whenever I'm speaking about a hyperbolic circle, it's going to be with an H. Okay, so the Euclidean one, of course, can be written in terms of the complex norm, right? And now my new one is, of course, in terms of my new distance, right? So what should be a hyperbolic circle centered at Z0 with radius R0? Well, it's those points in U whose distance to the center is constant equal to R0. Okay, I mean, it cannot be any other thing, right? And the theorem, which I also find very beautiful, is that if you give me, you see, for any Z0, you see, for any possible center and for any possible radius, if you want to compute the hyperbolic circle with this center and this hyperbolic radius, well, it actually coincides with this Euclidean circle, where you see here I'm writing the center as, you know, x0 x naught plus y naught I with this x naught and y naught in the real numbers. And so you see here in particular, somehow you see the only thing that changes is the imaginary part and the radius. So you see the hyperbolic center is this one, and the Euclidean center, it's in a way almost in certain way this one. At least it has the same real part, so it's aligned vertically with z naught, but with certain Euclidean radius. I'm going to draw a picture afterwards. But then this means in particular that every hyperbolic circle is an Euclidean circle. And from there one can very easily deduce that actually the hyperbolic circles are precisely those Euclidean circles that happen to be completely contained in U. Okay. So let's prove this theorem, which I also find very, very, very beautiful. And so first, notice this. I mean, of course, this is greater than this, right? Because to this I am adding something positive, and here I am subtracting that same positive thing. So of course this is positive, and this is also positive, right? And for that it's kind of you just check you just check, right? So for instance, you only need to check that this is positive, so you need to check that e to the r naught is greater than e to the minus r naught. So what you need is that e to the 2r naught is positive, right? But r naught is a positive real number, right? So this is, sorry, not positive, it's greater than 1. Yeah. But r naught is positive, so this is indeed greater than 1, right? Because this is e to the 0. And the exponential, at least restricted to the real numbers, is injective. Okay. Right, so this is indeed positive, and then also notice that this is the hyperbolic cosine, and this is the hyperbolic sine. Okay, so a hyperbolic cosine, hyperbolic sine, the inequality greater than 0. So that is preserved if I just multiply with a positive number, right? And then here, you see, here I'm taking this point in U, so the imaginary part, which is y naught, is positive. So of course I have these two inequalities. And this implies already that at least my Euclidean circle, which I'm signaling as a candidate to be the explicit computation of my hyperbolic circle, is completely contained in U, at least. Right? Because somehow, I mean, you stand here at this height, and this height is greater than the radius. So somehow indeed, right? You stand at a certain height, and that height is greater than the Euclidean radius. So when you draw the circle, you never leave U. Okay. Okay. Now I go to just kind of the brute force computation. So I know that the hyperbolic cosine is injective on the positive real numbers, not on the whole real numbers, but at least on the positive it is injective. And so that means that, you see here, since you see this is positive and this distance is always positive. I mean, I'm asking about those that satisfy that this distance is positive and is equal to this. It is equal. Then it is equivalent, since the hyperbolic cosine is injective on the positive real numbers. Then asking about the z's in U with this property is equivalent to asking about those z's such that the cosine, the hyperbolic cosine of this is equal to the hyperbolic cosine of this. Because here I'm dealing only with positive and only with positive. Okay, so that's exactly what I just wrote here. Right? That, instead of, you see, it's equivalent asking about the equality this equal to this. That's equivalent to asking about the equality this equal to this. Okay, now this identity, this equality, so the right hand side, I leave it as is. The left hand side, I substitute with my description, right? I have this formula which tells me hyperbolic cosine of distance can be replaced with 1 plus square of the difference of norm, square of norm of difference, 2 times imaginary parts. So that's what I do. But now is between this and this other point, but it's 1 plus square of norm of differences, 2 times imaginary parts. Okay, and I start developing it. And here for this I write my z's. I write them as x plus iy, of course, with the real and imaginary parts. And if I write z like that, then kind of I just develop, right? I mean, and here you see, here this is this one, yeah, and then here you have this other thing. Okay, now these 2 yy naught disappears with the minus 2 yy naught from the square, and so from this square only y squared plus y naught square survives, right? And then this survives, and this is cancelled. Right? Okay, and furthermore, this I can just move to this other side. All numbers involved here are positive, so no problem. Yeah, so this equality is equivalent to this equality. Okay, and now here you see in this equality, I notice the following. How to say? Here, so you see here, the point is that I have 2y naught, which kind of it gives me the idea of coming from some square, right? But there's this cosine of r naught. But you see, if I move it here, you see I have y square, which kind of contributes this part, and I have y naught square, which kind of would contribute this part, but then I kind of would be missing this cosine of r naught. So I want cosine of r naught square to appear. So I force it. And how do I force it? Using some identity that involves cosine of r naught square. Which identity? Well, I know the basic identity that this is equal to 1. So this 1, I rewrite it like this. Okay? Because when I write it like that, you see I can move this to the left and this to the right. And when I do that, so to move this to the right, I have to multiply with y naught square. Okay, move to the right. This one moves to the left, and I completed a square, and it's this square, right? And the point is that once I'm here, you see, this is the points in U that live in this Euclidean circle, right? With which center? Well, x naught plus y naught cos hyperbolic cosine naught I, and this radius, well, the square root, the absolute value of the square root of this. which is this. Okay, but we already the first thing we verified was that this was indeed contained in U. So this intersection is just this. So I'm done, right? So my hyperbolic circle is indeed what I claimed. Right? So in particular, every hyperbolic circle is an Euclidean circle, and then I leave you as an exercise. Now, if you give me an Euclidean circle contained in U, it is indeed a hyperbolic circle. I mean, so now what you have to do is, now what you are given is the Euclidean radius and the Euclidean center and the Euclidean radius, and you are given as hypothesis that the circle is contained in U. And now what I want you is to find the hyperbolic center and the hyperbolic radius. Right? So it's okay. So it looks like a calculus exercise, right? Okay. Now, how do things actually look like, right? So I would say that the picture is really beautiful. So here is my hyperbolic center. Remember that we saw that hyperbolic cosine. Just 1 second. Right. Yeah. No, I mean here hyperbolic. The point is hyperbolic cosine is always greater or equal than 1. Right. Because you see, hyperbolic cosine is something plus its inverse divided by 2. Remember, we studied the function something plus its inverse at some point when we classified Mobius transformations in terms of the trace. And so that function appeared, and we proved precisely that that something plus its inverse square was greater or equal than 4. So something plus its inverse is greater or equal than 2. So this is greater or equal than 1. So that's exactly what I wrote here. Okay, and so that this means that really you see the Euclidean center always lies above the hyperbolic center. So what you are seeing here always happens, that the Euclidean center lies above. Right? How farther above? Well, it depends on it depends on how big the hyperbolic radius you want. Right? The bigger it is, the bigger this becomes, and so the bigger this difference becomes. Right? Because hyperbolic cosine is increasing on the positive real numbers. And then here you can see the relation between the radii. So you see the hyperbolic radius is the length of this segment. So what's this segment? So what I did was, from this center, I just drew. You see, how do I say it? Yeah, from this point, I just drew the vertical line here, and then drew the circle with the Euclidean circle with this center, so that I can guarantee that here you have orthogonality, just so that one can guarantee that this is a shortest curve. And being a shortest curve, you see, from this point to some point in the circle, in the hyperbolic circle, this length is the actual radius. The hyperbolic length is the actual radius. Yeah. Okay, and so you see here there's something funny. So actually, because of how I constructed this circle, you can see that the tangent line to this circle at this point is actually horizontal. And now here you have another horizontal line. So something funny that happens is that if from the Euclidean center you kind of throw a horizontal line, Euclideanly it remains horizontal, But if you throw a horizontal, now shortest curve from the hyperbolic center, somehow that doesn't remain horizontal. It's kind of it somehow starts falling onto the real axis, kind of falling onto the real axis, falling to r bar. So somehow what I'm saying is that somehow it seems that when you start drawing shortest curves in U, it seems that the shortest curves are always somehow like kind of attracted to just r bar. Okay, so let me show you also some animation so that you can see circular motion with constant angular rapidity, angular speed. So for instance, if this I think you are very used to thinking in kind of in Euclidean terms, right? I mean, it's kind of just take the tire of a bike, right? And if the bike is going at constant speed, so the tire actually moves with constant angular speed, and then it's kind of it turns around its center. So I'm going to see the same thing, but in the hyperbolic plane, right? As if the tire were actually kind of lived in the hyperbolic plane, and one is seeing the hyperbolic center. So for that, I choose some center. And so you see there, you can already see somehow this phenomenon that I mentioned earlier, which is that it seems as if when one gets close to the real axis, the motion is Euclideanly slower, and when one gets away, it gets kind of faster. Right? So maybe let me show another time. So it looks like faster, and then slower, and then again fast, slow. But when I say fast and slow, it's kind of again when I see things with the Euclidean eye, right? Because when I see things with the hyperbolic eye, the distance was always the same, right? So there really wasn't like a difference in going faster or not, and the motion was with constant angular speed. So somehow, okay, so this gets maybe a bit too blurry, but so you see, it's kind of more or less the angles are always the same. That's the point. Okay. Okay. So let's keep going because. So let me yeah, I think I have an animation for that. Yeah, I think I have. So let's see. Right. So here. Okay. So let me show you. So here you see what I did before. Let me do it again. Is I can give you the initial point of my shortest curve and the final point, and then I want to see how the shortest curves looks like when it's traversed with constant rapidity. And we saw that this is how it looks like, and this intuition that fast, and then slow, until it finally arrives, right? Okay, but then there's this more like a sort of differential equations approach, which is give me the initial vector, the initial point, the initial conditions, right? The initial point and the initial tangent vector. So somehow what you are seeing here is the tangent plane anchored at that point. And let's say I want to go here, so it should look like kind of a vertical, right? More or less vertical, and that it has to start going to the right somehow. Yeah, and then of course I have to stop it because otherwise it will never stop. So I have to tell the program to stop. So let's see here, and let's say around here, and then to the right, and then here, etc. Okay. Anyway, that's not what you asked. What you asked was this. I'm going to do the same, but now you are going to see how the circle develops. That is, you are going to see how this R naught that you asked about, how it really, when we let it increase, how the circle looks like. Okay, so center, and then let's say here. Yeah, okay, so that was a bit. Okay, sorry. And again. Yeah, maybe a bit faster. So let's see. You see, and then kind of it starts looking more like this, right? I mean, if I do the zoom in here, it's like, okay, it really looks like similar, right? So let's say here, and again, that's the point, right? But if I zoom in, okay, if I zoom in, you can already see there some floating points problems. But anyway, but so is it clear now?
Yeah.
Yep. Okay. So, which, by the way, that's how it would look like. For instance, if you were in a pond, right? And then, but the pond was actually like a hyperbolic surface, right? And then you throw a stone, and then the wave, how would it look like? Well, just like what you just saw. Okay, so now let's move on to finally kind of starting to study the full group of isometries, which is something that somehow I didn't quite manage to do in the hyperboloid. So if you remember, in the hyperboloid, I only gave inclusions, right? And I only proved that certain groups, namely the orthochronous Lorentz group and the restricted Lorentz group, are contained in the group of Riemannian isometries of the hyperboloid, but I couldn't prove equalities. Now I'm going to be able to do it. Yeah. And somehow the basic idea is the following. Like, first, we're going to be able to express any arbitrary Riemannian isometry of the upper half plane through an explicit formula. Right? Kind of, you see, for the Mobius transformations that preserve U bijectively, we know the expression alpha z plus beta divided by gamma z plus delta, where we know that the matrix alpha, beta, gamma, delta can be taken to be a 2x2 real matrix of determinant 1. Okay, but now for arbitrary Riemannian isometries, we don't yet have such a formula. That's the formula we're going to develop. And then using that formula, we're going to actually see the full description of our groups, let's say of our groups, let's say as here as a Lie group, let's say. Yeah, and so just a reminder that I'm already, with no apology, identifying this group and the group of Mobius transformations that preserve U bijectively. Okay, now exercise. There are some Riemannian isometries that actually do not belong here. So this is the group of Riemannian isometries of U that preserve the orientation. So let me say some words maybe about orientation. And here I think it's more clear what I mean in the case of the upper half plane than in the case of the hyperboloid, kind of because this is already kind of nicely located within C. So somehow it's easier to get convinced, at least of some intuition. Okay, so let me I don't know, let me draw. Yeah, so right. Yeah, okay, so it's not okay. Drawing on the fly is not my strength, but okay. So let's say that what you have there is really U, right? So let's say that this is the x-axis, let's say, and this is the x-axis. I mean the real axis. Okay, and let's say that we have some diffeomorphism. Oops, some diffeomorphisms here. Diffeomorphism here. Let's say F, and let's say that this is a diffeom. So infinitely differentiable, kind of to avoid any kind of technical problems. And now what's my intuition about what it means to preserve the orientation? My intuition is that if you draw a small circle and you kind of and you draw a small circle here and you parameterize it, let's say in the counterclockwise sense, let's say using the usual cosine and sine. When you apply F, well, this is going to be, well, maybe not a circle, but it's going to be a closed curve, right? Somehow this closed curve, if you want, by the Jordan separation theorem, splits the upper half plane kind of into a bounded and unbounded region. Yeah, so I can consider what the bounded region, and then with respect to that bounded region, I can say, okay, is it the orientation? You see, when I apply this followed by F, the corresponding orientation, is it clockwise, counterclockwise, or not? Right? And somehow my idea, the intuition is, if it is, then I say that it preserves the orientation, that F preserves the orientation, and if it doesn't, you see, if it doesn't match, if here I have this one parameterized counterclockwise, but this turns out to go around the bounded part counterclockwise, then I say, okay, it doesn't preserve the orientation. Okay, so that's kind of the intuition. Right? Now, of course, this intuition, being just intuition, has its troubles, because I would have to really answer many questions, right? It's like, okay, so if you have one diffeomorphism, how do you know that it doesn't happen that sometimes it preserves, but if you move away, it doesn't preserve. Right? How do you know that this is a uniform behavior, right? And so on. One of the points is that somehow this behavior is can be kept one can keep track of that by looking at the sign of the determinant of f at any point. So not of f, of the derivative of f. So f is a diffeomorphism, so its derivative is invertible at every point. So it has non-zero determinant at every point, and then somehow one would have to prove that the determinant is either always positive or always negative, right? No matter at which point I take the derivative of f. And second, which is, I would say, the harder part, one would have to get convinced that somehow this intuition, you see that this intuition corresponds to, you see, when the orientation, this sense of the curve is preserved, corresponds to the derivative always having positive determinant, and when it's not preserved, to the derivative always having negative determinant. So that's kind of the, and this at least in my viewpoint can be something very subtle, very not so easy to get convinced of. Okay, but so somehow I'm just going to take it as a black box, right? That somehow the what keeps track of this intuition is the sign of the determinant of the derivative. That's one thing, and then second, like for instance, this at least is somehow consistent with, let's say, take just a Euclidean reflection along a vertical line, right? And then let's say draw the image of this one along that one. So the image would be, you see, let's say I draw the image on the right. Right? The image would look like, well, something like this, but now like this. Right? And now here you can see what I was saying. No matter what circle I take, right? If I decide to traverse it counterclockwise, its image is traversed then. Oops, sorry about that. Is traversed. Let me see, not to get confused. Yeah. It's traversed then clockwise. Right? And if you look at the determinant, it's always -1. Right? So if you look at the determinant of the derivative of the function, which is reflection along a vertical line, the derivative is always -1. Right, negative. Okay, so that's some words about orientation. And you see, and then here in this exercise, when I say not belonging to this one, what I mean is that this one, which by the way is actually an Euclidean reflection along the imaginary axis, is a Riemannian isometry, but the derivative always has negative determinant. That's what I mean. So in other words, when at least in this course, when you want to argue about orientation, you don't have to worry so much about kind of convincing me of the intuition, but kind of you can just focus on, okay, let's deal with the determinant of the derivative, and that's it. Because as I said, the discussion about how the determinant corresponds to the intuitive idea, I think it can be a subtle conversation. Okay, now coming back, right? Remember, I want an explicit formula for arbitrary Riemannian isometries of U. Okay, now some more exercises. This, which is kind of a refinement of what we have done already. So take 2 points in the positive part of the imaginary axis. So it's kind of, so it's my 2 points, W0 and Z0, right? And then take any other 2 points in U. I don't know, any 2 points. Let's say W1 and Z1. Yeah, and then prove that if this distance between them, if the hyperbolic distance between these two is equal to the hyperbolic distance between these two, then there is one Mobius transformation mapping this one to this one and this one to this one. So I would say that then kind of somehow this segment is congruent with this one somehow. Yeah, and this Mobius transformation also kind of, not any Mobius transformation, but actually a Mobius transformation preserving U bijectively. Right? So this we pretty much already did this exercise. It's just kind of for you, it's kind of a reality check. Okay, another exercise. If you give me a Riemannian isometry of the upper half plane, and it happens to fix 2 distinct points in the positive part of the imaginary axis, then it fixes every point in the imaginary axis. Right? So you give me a Riemannian isometry, and somehow for some reason I can show that it fixes 1 point here and another point here, both in the positive imaginary axis. Then what I can deduce automatically, because of this exercise, is that it fixes every other point. So this point is also fixed, this etc. But for the positive part of the real axis, I cannot guarantee it for the whole U, because it could be that it's a reflection, that somehow this is sent to this, for instance. So, but I can deduce it at least for the positive part of the real axis. Okay. Okay. And now, and this exercise is also not very hard. It's not very hard, but somehow it requires you to really have kind of a working knowledge of how to deal with Riemannian isometries, at least on the basic level. Okay, so now I'm going to take all these exercises for granted, and take an arbitrary Riemannian isometry phi, and then and pick 2 distinct points in the positive real, in the positive part of the imaginary axis. 2 distinct points. So somehow I have my 2 distinct points, right? Okay, and now I apply phi to these 2 points, right? So let's say that this is W0 again, and this is Z0, and I apply phi to each of them. Right? So I don't know, phi of Z0 and phi of W0, let's say, right? And so something I know is that there exists a Mobius transformation sending this one back to Z0 and this one back to Z0. Right? So I take that one, and so somehow what I would wish is that Mobius transformation is actually the inverse of phi, but that's not always going to be the case. But so you see, at least what's the idea? That by sending these points back, I will automatically know, because of this exercise, that the composition fixes all of the positive part of the imaginary axis. Okay, that's what it's here, right? I mean, because it fixes, you see, that composition. You see, nu sends them back, right? Nu sends this one back. Nu sends this one back. So this composition fixes all the positive part of the imaginary axis pointwisely. Okay. And now I want to see what's the behavior outside the positive part of the imaginary axis. Because here I already know the behavior therein. Right? So I take any point outside, and I write it in terms, you see, as A plus BI, and its image on their decomposition. I also write it as positive as C plus DI. Okay, and now I'm going to do. Now here comes kind of some magic. So I take an arbitrary positive real number, right? And then I notice the following. So this we computed, right? This was the formula for the hyperbolic cosine of distance between lambda I and W, and it gives me this, right? And when I compute in terms of this expression of W, what I obtain is this, right? For instance, imaginary part of W is B, imaginary part of lambda I is lambda, right? And this one, you see, this one is purely imaginary, so lambda minus B square, and then A square, right? Because here this one is purely imaginary. Okay, and now since nu preceded, you see, this composition, nu preceded by phi, is a Riemannian isometry. Why? Well, because, well, I mean, it's actually, I already used it, but I repeat it, right? Because phi is a Riemannian isometry, and nu, being a Mobius transformation that preserves U bijectively, is also a Riemannian isometry. So nu preceded by phi is a Riemannian isometry, and so that means that if I take these 2 points and I apply nu preceded by phi to each of them, this doesn't change. Right? The hyperbolic distance between them doesn't change. But nu O phi, this one, fixes this point, and of course sends this point to this one. So this distance is equal to the distance between the images. So this hyperbolic cosine is equal to this hyperbolic cosine. And now this one I can also compute using how I wrote the image of W. And then you see it's kind of completely analogous to how I computed this one in terms of W. I get this. Okay, so just again, so why is this distance equal to the distance when instead of this I write the image under a Riemannian isometry and the image under that same Riemannian isometry? Well, because this is the infimum of hyperbolic lengths of curves, right? And a Riemannian isometry preserves the length of each curve, so it preserves the infimum. Okay. Now, what I obtain from this is that this is equal to this. So, okay, so the one cancels, right? And what I obtain is this equal to this. Okay, now lambda was positive, so these 2 lambda cancels. Yeah. And then I expand this square. Okay, and I expand this square, and you see, and then and moreover, this moves here and this moves here, and so here with this d, what I obtain is minus 2 lambda b d, and here with this b here, I obtain, and here there should be a square. There should be a square. And here what I obtain is minus 2 lambda d b. So in both sides I have this, so I can cancel it. So what I obtain is this equal to this. And you see all of them are positive real numbers. Right? I mean, you see this one lies in the upper half plane, so D is positive, B is positive, so D is positive, B is positive, and whatever else appears square. Okay, so I can just divide by this one, and I obtain this equality. Okay, and then what? And then the point is that this equality holds for every positive lambda. So I can let lambda go to infinity, and you see here in terms of lambda, this is constant, this is constant, this is constant, this is constant. So in terms of lambda, this is a polynomial of degree 2 in lambda, polynomial of degree 2 in lambda. When lambda goes to infinity, the limit is d divided by b. And so d divided by b is 1. Okay, so b is equal to d. Right, so b is equal to d. And moreover, so first, b is equal to d. So what does this mean? It means that w and this guy sit at the same height. Right? I mean, I don't know exactly the relation between them, but now I know at least that they sit at the same height in the upper half plane. Okay, but I also can go back to this equality, because now I know that b is equal to d, so this cancels, and this cancels. So a star is equal to c star. And this means that one is plus or minus the other. So here you see here, what can I see? What can I say? Okay, so I have the x-axis, imaginary axis, and somewhere here is w, and you see they sit at the same height, this and its image, and either a is equal to c, in which case w is equal to this, or a is equal to minus c, or if you want, c is equal to minus a, in which case w sits, it's kind of precisely the Euclidean reflection. Right? So I know for each w, I know that the relation between w and its image is that it is either itself or the other one. Okay, now, which is this, which is what I'm saying here. Now there comes a subtle point. This is for each w, I know that either this or this happens. But that right now is kind of, I am at the moment where I have to realize that a priori it could happen that for some it's the first situation, and for some others it's the second situation. I really have to argue more to say, okay, for all points is the first, or for all points is the second. You see, because these computations were done completely in terms of w and its image. If I change this w, how do I know? You see, I mean, it's not going to be the same ace. It's going to be another computation. So how do I know that I'm going to arrive at the same type of conclusion if I take another w? I have to prove it. So that's what we're going to do. We are going to do next. I mean, by the way, this is something that in some books they don't realize that there's this problem. But anyway, I mean, they just jump into the conclusion, right? Okay, so this is either the identity or the other one. But okay. Anyway, now the point is this: consider kind of the part of the part of the upper half plane, kind of which has positive real part, right? So U is like this, and then U plus is this part. Okay, it's kind of half U. Okay, and consider the sets. Consider the following sets. The set of points in U that are mapped to themselves by nu of phi, and the set of points in U plus that are mapped but not to themselves but to their reflection with respect to the positive part of the imaginary axis. Right? So in other words, I'm saying here is U plus, and A consists of those points here that are fixed, and B consists of those points here that are not fixed, but rather go to the other side. So exercise, each of these is closed. Okay, and this is connected. Right? So one of them has to be empty. So the other one has to be the whole U plus. Okay? So so at least I know by connectedness that either everything here is fixed or everything here goes to the other side by connectedness of U plus. Okay, but you see now if something here is, if everything here is fixed and I take a point here, I know that this point is either fixed or it goes here. But my function was bijective, and this was already fixed. So it must also be the case that this is fixed if everything here was fixed. In the other case, if everything here goes here, then whenever I take something here, it has to go here because otherwise it would be fixed and my function wouldn't be bijective. Okay, so now because of the connectedness of U plus and bijectivity, by the bijectivity of nu preceded by phi, now I can guarantee that the conclusion I arrived at is uniform. In other words, that either every element, every point is fixed, or every point goes to the other side. Okay. In the first case, what I obtained is that phi was the inverse of this one. So somehow in the first case, what happens is that the Mobius transformation that I chose to send them back is precisely the inverse of phi. In the other case, if this happens, well, then I take a matrix representing the inverse of nu. I know that nu is a Mobius transformation, so I know that nu inverse is a Mobius transformation. So I know that nu inverse is of the form mu a, for some a. Okay, and now from here, you see from here, what I deduce is that phi of w is equal to nu inverse of minus w bar, minus w conjugate. Right? Okay, and this one, well, nu inverse is just, I apply the Mobius transformation, right? It's alpha times this plus beta divided by gamma times this plus delta. Yeah. Yeah, so you see the point is here. Oh, right. Okay. Yeah. So. Yeah. I mean, once you have this equality, then you just apply nu inverse, right? Yeah. And then. Right. Okay, and then once you are here, then you just apply the rule of having a Mobius transformation. And this minus comes from this minus. This minus comes from this minus, not from the matrix. In any case, you see, if if when I took the Mobius transformation that moved my points back, this nu, then maybe I wasn't lucky enough that I was actually hitting the inverse of phi, but still I'm able to obtain this explicit formula for phi. Look, phi of the point is this. So in any case, I succeeded. And now one more thing. Since A has determinant 1, the matrix formed by minus alpha, beta, minus gamma, delta has determinant -1. So somehow my phi that was not equal to the Mobius transformation can still be expressed somehow in terms of with a Mobius-like expression of a matrix, but now it's kind of a modified Mobius-like expression because one has to conjugate, and also one does it for a matrix of determinant -1. Okay, but it's better than nothing, right? I mean, and so somehow the theorem is that we just proved is that if you give me any Riemannian isometry, then we are in exactly one of two situations. Either the Riemannian isometry is just a Mobius transformation in PSL2R, right? So just a Mobius transformation preserving U bijectively, coming from a matrix, from a real 2x2 matrix of determinant 1, or is of this this arbitrary Riemannian isometry is of the form modified Mobius transformation, but associated to a matrix of determinant -1. Right? So here, of course, I already made a change of variables, right? So that the minus sign is already hidden here. Okay, so this tells me whatever Riemannian isometry you give me, you see, there is it can be expressed in an explicit way. Right? And second exercise, if anything of this form is a Riemannian isometry. We already proved that anything of this form is a Riemannian isometry. Now you have to prove that anything of this form is a Riemannian isometry. But you see, it amounts, if I consider this other expression where now the matrix has determinant 1, so it kind of, if I decide not to hide the sign here, you see, it's a Mobius transformation applied to something. A Mobius transformation, I already know that it's a Riemannian isometry, so I only need to know that sending W to minus W conjugate is a Riemannian isometry. But that's precisely the exercise that I left, that I told you. Okay, which by the way is an exercise to hand in. Okay, and then here in this exercise, I'm not including the part about orientation, just kind of not so that you don't get stuck thinking about that. Right? So, okay, now the corollary is that you see all of this preserve orientation, none of this preserve orientation. Well, of course, here I'm pointing at this. I should really be pointing at the derivative, at the determinant of the derivative of this. But in the end, that determinant can be written in terms, is going to be a positive multiple of this guy. So it's also going to be negative. Anyway, these preserve orientation, these do not preserve orientation, and it's all of them. It's all of the possible Riemannian isometries. So these ones are precisely all the ones that preserve orientation. That is, finally, we are able to do something, to give the full group of isometries that preserve orientation. And then the final part is to try to give a description of the whole group of Riemannian isometries. Okay. So definition, you see I enhance SL2R to this S star L2R, which is just the 2 by 2 real matrices of determinant 1 and -1. This is still a group, right? I mean, it is still a subgroup of GL2R. Okay. Now, this theorem tells us from any matrix in S star L2R to any such matrix, you can associate a Riemannian isometry. So you have a function, and it's surjective because every Riemannian isometry is of that form. Okay, exercise. It is a group homomorphism with this kernel. Oops, here I should say plus minus. I'm sorry. Okay, and I think I'm going to stop there because I ran out of time, but I was almost finished. So next time I just finish with the whole computation of the isometry group. Okay, so I'll see you on Monday.